Hello and welcome. Today I'm going to explain why another name for light is electromagnetic radiation. So light is the same exact thing as electromagnetic radiation. And the source of all electromagnetic radiation is electrons, or charges in general. You can have protons moving up and down, which produces an electromagnetic wave, which I talked about a little bit about in the last video. So the person who gets the most credit for associating light and electromagnetic radiation is James Clerk Maxwell. And you might have heard of his equations before. So he has 4 equations. Before we get into those, let's talk a little bit about his life. Around 1860, the year 1860, is when he was looking at a few experiments from the past done by I don't know how you say it, Ampere, something like that, by Michael Faraday, by Biot Savart, probably. Who else was he looking for? Anyways, these guys, probably some more, and more, came up with some laws that were either electric in nature or magnetic in nature. And physicists had a inkling that there was some electric phenomena that was kind of connected to magnetic phenomena, but nobody could really pin down the connection. James Clerk Maxwell did a lot to connect those two ideas. So he realized that electromagnetic radiation propagates at the same speed as light, and he concluded that they're the same exact thing since they move at the same speed. So now we'll talk about his 4 laws, or his 4 equations. And I'll first speak about them in words or pictures, and then I'll write how you would see them in a math form. So, well, there's no specific number to these. I'll just call this one number 1. So number 1 is that if you have a charge, say an electron, inside a sphere, right? You have a sphere here. Well, the electron emits an electric field. It doesn't emit an electric field, but it possesses one in some sense. And you can represent an electric field with arrows or lines. And if you have a sphere in space and you measure the electric field going through that sphere, that tells you how much charge is inside. So I'll say that again. If you have an imaginary sphere in space and you measure the electric field going through that sphere, you can tell how much charge is inside that sphere. So being a little more mathematical, the flux, the electric flux through your sphere is proportional to the charge inside of your sphere. And how you would see it in a math form would be the divergence of the electric field is equal to the charge density divided by a constant called the electric constant, or the electric permittivity. I always forget if it's permittivity or what's the other one? The other P. It's not important. The second law says if you do the same thing, but for a magnet, you're always going to get 0 because there's no magnetic analogy to an electron. Right? A magnet has a north and a south pole. You can never get just a north pole or just a south pole. The analogy, so this is a magnet. The analogy with electricity would be you have a proton or any positive charge and a minus charge. So if you take just an electron or just a proton, you would call that a monopole. If you put two of them together, you would call that a dipole. So the second law says there are no magnetic monopoles, right? There are electric monopoles because you can have just an electron, but you cannot have just a south pole or just a north pole of a magnet. So in math, that says the divergence of the magnetic field is equal to 0. No magnetic monopoles. Alright, the next law. The next law says that if you have a loop of wire and you put electricity into that loop, so it's going around. Say it's going around that way, counterclockwise. And imagine turning this, right? Imagine turning this loop of wire. Then you're going to produce a magnetic field that points perpendicular to the plane of that wire. So right, if this loop of wire is sticking out of the page, well then the magnetic field, which is this arrow I've drawn here, will be producing up the page. Or if our wire's on the page, then the magnetic field is pointing up towards the camera. So if you want to write that in math form, you would say the curl of the electric field produces a changing magnetic field that changes in time. Now, it's kind of the flip side of the third law. It says if you have a loop of wire and you have a magnet, north and south, and you move that magnet up, well then you're going to produce an electric current going this way. So in math form, it says the curl of the magnetic field equals, you have some constants out here, and I think there's even a negative sign. You have a changing electric field plus a constant times the current density. So really, in words or pictorially, if you have a magnet and you throw it through an electric, or throw it through a wire loop, you're going to produce a current in that loop just for a short while. Now if you have a magnet and you keep putting it up and down through that loop, you're going to have an electric current that goes this way, then it changes directions, then it changes directions. So that's a brief overview of Maxwell's equations. Okay? Now, that we've been introduced to those equations, let's actually take a look at it again. So, the third one says that if I have a changing magnetic field, I'm going to produce an electric field. And similarly, the other one says that if I have a changing electric field, I'm going to produce a magnetic field. Right? So, changing E field, you produce a B field. Well, if you produce a B field where there was none before, you're going to produce an E field. And now that you produce an E field where there was none before, you're going to produce a B field. And so on and so forth. So, in that way, you get electromagnetic radiation. Because if you take an electron and you have it on a wire loop, and the electron starts going around that wire loop, well, then you're going to produce a magnetic field that wraps around that loop. And now that you produce a magnetic field, you're going to produce an electric field that wraps around that loop. So it's fields wrapping around fields wrapping around fields. And in this way, you produce a wave. An electromagnetic wave, which travels 300,000 kilometers per second. So, I hope you found that useful. Thanks for watching, and have a good day.